Let's take a look at the one piece of Ethernet that Rich Seifert developed in the 80s that has truly stuck around, and that is the Ethernet frame. This has not changed since 1982, and there's no plan on changing it in the near future either. Even for the bigger Ethernet specifications, we can still use this same Ethernet frame. This is ridiculously impressive in information technology. Truly impressive. The Ethernet frame has been around and survived through so many iterations of data networking. I can't tell you how impressive it is. Just been around for the lifespan of modern networking as we know it. At any rate, let's look at how this is constructed. So the first two fields in this frame are the destination MAC address and the source MAC address. Now we put the destination MAC address first for a good reason. I'm going to learn about that in a second when we talk about how switches operate. But the MAC address now is a 48-bit value that is composed of two parts, a manufacturer ID and a serial number. Now the manufacturer ID, what happens is if you're a manufacturer like Intel and you want to make network interface cards, you apply to IEEE, you pay a fee, and you get this manufacturer ID portion of the address. It is the first 24 bits of the address, and it is written in hexadecimal. And hexadecimal is pretty nice. It's translated, each value of hexadecimal is translated into 4 bits. So what I've done is I've just written out in binary the MAC address right below the hexadecimal representation of it. The second half of the number here is the serial number, and this is what the manufacturer will assign to each individual network interface card. And the idea behind this is that every single network interface card on Earth will have a unique MAC address. Notice I said the idea behind this is that for some reason errors happen surprisingly more often than you might think, although you don't get to experience this very often. I think in my career of about 15, 16 years now, I've seen one, maybe two cases where we've had the same MAC address on two devices that were both connected to the same network. It's very unusual. But the idea here is that every single MAC address on Earth is unique, so you can take any network interface card and plug it into your device and it'll be a unique identifier on your local area network. Now this is the layer 2 address. Windows calls this the physical address. Some people call it the hardware address. Usually it's referred to as the MAC address, the media access control address. All right, so we put the destination MAC address first, the source MAC address second. Where we're sending it to goes first, who's receiving it goes second, and then we have this type field. Now the type field is designed to accommodate a message, essentially, to the next layer up. So the type field is a message to the network layer saying, hey, I'm about to send you this type of packet. So it will specify, in modern networks, it's going to specify either IP version 4 or IP version 6. And it's going to put one of these two codes in there, either 0800 or 86DD. Now I put the 0x in front of these numbers, and which is traditional to indicate hexadecimal. So 0x and then a number indicates hexadecimal. We ignore the 0x portion of it. It just is a notation saying, hey, the numbers that are following this are in hexadecimal format. I put the binary representation of that right next to it there as well. Now, this field was much more important in earlier years of networking because we had a lot more network layer protocols we could use. Back in the day when Novell was popular, Novell used a network layer protocol called IPX. So you had IP and IPX. You had XNS. You had several other versions of network layer protocols that we could use that have all mostly gone defunct. So we're left here with only two different protocols, either IP or IPv6. The nice part about this is it lets us use Ethernet at layer 2 to send pretty much any type of layer 3 packet we want. So remember, during the encapsulation process, we stick this packet inside of our frame, and we put this header and footer on our frame as the encapsulation process. So really we're just specifying with the type field what layer 3 protocol is being used. This last field, the FCS, well, there's lots of three-letter acronyms in networking, if you haven't noticed already. FCS is another one, and there's another one built into there, and that's CRC. So FCS is the frame check sequence. And what it does is it uses this mathematical concept called a cyclical redundancy check. And it uses that to create a hash. Now, a hash is pretty simple. It's just a short number that is a unique identifier for a much bigger set of data. So we run this formula, and it essentially looks for remainders in numbers and records the remainders. And you don't need to know how to do this unless you actually are going to be designing network interface cards or troubleshooting Ethernet frames at a very low level. But what it's doing is it calculates a number. And then it puts that number into this 32-bit field at the end of the frame. So we run a calculation against this entire piece of data, we come up with a value, and we stick it at the end of the frame. And then we send the frame out. This way, when the frame is received at the other end, the switch or the receiving device can then run its own calculation against the data that was received and compare it to the value that's in the FCS field. If the values match, the frame has integrity, meaning that the frame sent is exactly the same as the frame received. If the FCS values do not match, that means the frame does not have integrity, something modified the frame in transit, and it should be thrown away. Well, what could modify the frame in transit? Could be interference, could be degradation from the router. Router could be dropping packets. The link that we're sending it over could be poor, and we're dropping information in there. So the data may get corrupt over the wire, and this is a mechanism to check to see if the data was corrupted. The bad part about this is there's no mechanism built into Ethernet to re-request the missing information. That actually takes place at other layers of the OSI model, and if you remember correctly from previous slides, there's one protocol in particular that does checking for lost data and asking for missing data really, 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 really well. And it's the foundation of networking at the transport layer, right? That protocol, if you remember, is TCP. So TCP is going to do our requesting for missing segments should our FCS value way down at the data link layer, should that fail. So should we not get a frame, we're going to use TCP up at the top to make sure that we re-get the data that we're missing. Okay, so that's how FCS works.